Well, good morning, everyone. Welcome to this. I believe it's the second event in our lead up to WWETT 2020, which takes place in Indianapolis next year. You'll see there on the top banner, it's in February. Board Chair Oliver Greaveson, who's with ZTech and also WIPEC and a whole bunch of other water industry organizations, will be speaking on 2 days with a track about smart water and smart wastewater. Today our guest is Dr. Karina Carpentier. I hope I'm pronouncing that right, with the Sensileau Sensor Platform, because we make a lot of decisions about infrastructure, about planning, about management, about how to control what can sometimes seem totally uncontrollable. And the biggest contributor to that is knowing what's actually happening. So at this point, Karina, I'm going to stop my video camera and turn it over to you to introduce yourself.
Thank you very much, Dendra. Good morning, everybody, or good afternoon, wherever you are. And thank you very much for tuning in to this webinar. Dendra invited me to do this presentation to talk to you about 7 proven ways to save money and improve sustainability without making huge investments, with the subtitle Using Sensor Technologies to Optimize Wastewater Processing. And I'll start by telling you a little bit about me. I have a background in ecology, aquatic ecology, and ecotoxicology, and I have worked as a researcher and consultant in water quality monitoring for the last 25 years. And all the knowledge I have collected over the years comes together in the Sensileau Sensor Platform that I established with my partner Jan Broos in August 2017. So the Sensileau Sensor Platform covers a wide range of topics, from drinking water production and distribution to wastewater collection, processing and discharge. Today we will focus specifically on the optimization of wastewater treatment processes. Our starting point is the assumption that most wastewater utilities currently use only conventional treatment technologies, such as active sludge treatment, that aging infrastructure and an aging and thus shrinking workforce further complicate effective wastewater processing, and that funding for updates and upgrades of treatment plants is hard to come by. Against this background, we will explore 7 ways to save money and reduce the carbon footprint of the treatment plant without making huge investments. And here they are. In this webinar, we will look at the automation of influent monitoring, the optimization of active sludge treatment, possibilities for resource recovery after stabilizing effluent quality, the optimization of water quality monitoring programs, the effects of automated processes on staff workload, the use of robotics to prioritize underground asset maintenance, and of course the benefits of joining the Sensileau community. The first case concerns the automation of influent monitoring. Many wastewater utilities currently do not make optimal use of the available retention capacity in sewer systems. Depending on the type and nature of the wastewater collected, conventional active sludge treatment units may be at risk of toxic effects from sewage pollution. For example, when a company incidentally discharges large amounts of acid into the sewer as a result of internal cleaning operations. And when wastewater treatment plants are operating towards their maximum capacity, investments in new infrastructure to increase this capacity may seem unavoidable. However, The automation of Influent flows and quality monitoring, combined with valves to control the flow into the treatment plant, can ensure a more continuous flow through the treatment plant. Using the retention capacity available within the sewer network, heavily polluted waste streams can be diluted by waste streams containing cleaner water, thus reducing the risk of toxic effects on the active sludge. This results in a more stable effluent quality. Too far. Back a bit. The example shown here is of the wastewater treatment plant at the city of Eindhoven in the southern part of the Netherlands. Eindhoven wastewater treatment plant is fed by three main sewer lines. One coming from the built-up area in the city of Eindhoven, one covering the northeast of the city, and the third one covering the southern part, the area south of the city. In this case, pH measurements within these three main compartments were performed to track quality changes within the sewage. The graph on the left shows that at some point pH dropped by almost 2 points from 7.4 to 5.6 for several hours within the flow coming from Eindhoven city, the red line. The flow from the area south of the city, indicated by the green line in the graph, did not show a drop in pH level. The flow of the south part of the sewer system could thus be used to dilute the Eindhoven city flow, and the pH shock to the active sludge bacteria could be avoided. Although the project is still ongoing, a few major cost and carbon savers have already been identified. The use of excess retention capacity in the sewer system has enabled the postponement of investments in expanding treatment capacity by several years, and as a result of a more continuous load of the active sludge unit, carbon source dosing could be reduced. Exact figures depend mostly on the current state of the wastewater treatment plant and the number of years by which major investments can be postponed. It is expected that an investment between $50 and $300,000 US can be recovered within a period of 6 months up to 2 years. At the same time, a carbon footprint reduction can be achieved, mainly because the reduction in carbon source dosing, which results in fewer truck movements. The expected reduction on the basis of our experience in the Netherlands is about 324 tons of CO2 per year, which is the equivalent of driving your car around the world 40 times. The second showcase demonstrates the use of sensors in plant automation of activated sludge units at wastewater treatment plants. Improved control and optimization of wastewater treatment processes offers the potential for significant savings of energy, chemicals, and carbon. Advanced process control technologies have been developed over the past years, and water utilities have trialed and installed either off-the-shelf products or developed their own in-house solutions. It is expected that the use of these systems will increase significantly in the near future. The drive within the water industry to save energy, reduce costs, and minimize carbon footprint has led to a focus on the optimization of wastewater treatment processes. Within a typical wastewater treatment plant, the aeration equipment used to maintain the required dissolved oxygen levels in the activated sludge process can account for as much as 60% of total plant energy use. Conventional fixed set points for dissolved oxygen control provide effective aeration of activated sludge units, but more sophisticated advanced process control, which uses inputs from sensor measurements, offers additional benefits such as reduced energy and chemicals consumptions and hence carbon emission, as well as improved plant stability and a more constant effluent quality. The main measurements used for wastewater process control are dissolved oxygen and ammonia. Sometimes also nitrate or phosphate is measured. Reliable and robust dissolved oxygen measurements is fundamental to aeration control and optimization of the activated sludge process. Poor dissolved oxygen measurement results in poor aeration control, leading to variable treatment and excessive energy use. When applied over a whole site, even relatively small errors in the instrument readings resulting from, for example, poor calibration, instrument drift or fouling, can add tens of thousands of dollars per year to treatment costs through excess energy use for aeration. Dissolved oxygen measurement has benefited from a genuine advance in technology in the past few years, and there's now a generation of sensors using optical techniques which potentially offer better performance and lower maintenance requirements than the traditional electrochemical technology. Ammonia may be monitored to control the supply of oxygen used for nitrification in the activated sludge process. In this application, the ammonia monitor is used as part of a feedback control to adjust the dissolved oxygen set point and hence the rate of aeration. There's also an application for feed-forward control, with the monitor positioned ahead of biological treatment. As with all wet chemical analyzers, correct installation of ammonia sensors in wastewater is crucial. Many wastewater utilities have mixed views on the benefits of the simplicity of the electrochemical probes versus the use of more complex colorimetric analyzers. Probe-type electrodes are generally considered more suitable for process control, in particular optimizing aeration. They work best at high ammonia concentrations. However, they do show drift and require regular calibration, typically every quarter. Additionally, nitrate and phosphor sensors can also be applied. This example of a wastewater treatment plant in Belgium shows that the number of blower hours was reduced significantly after the implementation of the advanced process control system. In this way, energy savings of more than 20% were achieved. The savings of energy and carbon derived from improved process control can arise due to various causes. A reduced treatment level will become possible due to improved stability of the treatment, resulting in less variable effluent quality. The energy savings that can be achieved by improved dissolved oxygen control depend on the plant loading characteristics, plant configuration, and the level of instrumentation. On average, a water management board in the Netherlands can save 20% on its energy consumption by optimizing its activated sludge process, thus resulting in an annual cost savings of about $240,000 per year. The anticipated initial investment cost of approximately $165,000 will thus be recovered in about 9 months. Aside from the cost savings, the implementation of sensor technologies for just this one part of the treatment process leads to a reduction of about 10 kilotons CO2 per year, plus an additional 25% reduction of the formation of methane and laughing gas, both potent greenhouse gases. The yearly carbon footprint reduction associated with this activity has been estimated at 438 tons of CO2, which is the equivalent of 442 passengers flying from London to New York. The main driver for installing advanced aeration control is energy saving, but a significant benefit of a successful advanced control system is improved plant stability, resulting in reduced effluent variability. And a more stable effluent quality offers improved potential for the recovery of valuable resources such as phosphates. The example you see here is of a Dutch wastewater treatment plant in which phosphate sensors were placed right after the aeration tanks. The graph shows a much more stable effluent quality after the implementation of the advanced process control system, which is from about here. And before that, you see the phosphate concentrations are much more variable. But this is only the beginning. Aside from the cost savings that can be achieved, resource recovery can be converted into a profitable business. Both Europe and various states in the USA are working on legislation to facilitate the recovery of valuable resources from wastewater and to make it legally possible to sell recovered products or half products. Here you see one of the many innovative initiatives to recover valuable resources from wastewater, in this case the iron phosphate mineral vivianite from digested sewage sludge. This is achieved through an innovative magnetic separation technology. An investment of about $150,000 will cover the sensor technologies, staff effort, and data analysis necessary to achieve a more stable effluent quality and optimized operations. This in itself results in about $125,000 in cost savings per year, leading to a return on investment of about 1.2 years. The phosphate recovery unit shown here is not included in these figures, as this possibility depends on legislation being in place which allows for a wastewater utility to generate revenues from recovered resources. However, units such as shown here are expected to have ROIs of between 5 and 10 years. In addition, a considerable carbon footprint reduction can be achieved as well, which can increase even further if the actual phosphate recovery is included. Then we get to number 4. Sensor technologies are available for monitoring a variety of parameters in water or during treatment, and some have been used for many, many years. As a result, many utilities often have a wide variety of instruments installed. This was also the case at the utility of our example here. Online water quality monitors were used for process monitoring as well as research purposes, and each user was responsible for the maintenance of their own instruments. As a result, a great diversity of sensors had been installed, but maintenance was performed ad hoc, if at all. This led to unsatisfactory performance of the online instruments. Periodical verifications consistently showed the sensors were not performing well, leading to a lack of trust in their results from the process operators, who therefore relied on daily measurements with portable instruments instead of the online data for determining their process settings. So how did this happen? One factor involved turned out to be the procurement process. The implementation of monitoring systems is often done incrementally over many years. Some of the instruments have been installed as part of large capital projects in which the instruments are selected, installed, and integrated by specific contractors. But utilities are often public organizations, so projects need to be publicly tendered, which means that sometimes the decision for a certain solution is based on other factors than that which best suits the application. This might be cost, but it could also be that the sensors are included in a bigger package and the priority is on other aspects. Sometimes maintenance is included in the procurement contract with the suppliers, but in other cases, maintenance is performed by the utility's own operators or part of a long-term contract with an engineering consultant. It can also mean that there's little continuity as contractors change, instrumentation changes, and this can all hamper the development of well-established and standardized operation procedures and embedding them in the organization. These aspects often result in many different products being used at a plant, which complicates maintenance and stocking spares. In order to tackle this problem, our example utility initiated a project to centralize the remote control of treatment plants. This development from decentralized semi-manual control at each individual treatment plant to centralized remote control of the treatment plants within the span of a few years was driven by an increasing pressure to improve the efficiency and economy of operations while at the same time ensuring the quality of the water produced. This was made possible by the development and implementation of a robust quality assurance and quality control strategy for the online monitors that this unstaffed operation relies on. First, an inventory was made of the sensor systems in use and the data they produce. All systems whose data was not used were taken offline. For the remaining sensor systems, standardized maintenance and calibration protocols were developed, and a routine maintenance and quality assurance process was implemented. Our example utility started with all the pH sensors first, and then extrapolated the procedure to other sensor types as well. Apologies. Where are we? By following this procedure, the utility was able to structure the management and operation of online sensors with the support of the water laboratory. The instruments were performing well, were subject to a well-organized maintenance regime with periodical verification by an external laboratory. Due to the success of the approach taken, the online monitors were even accepted into the accreditation scheme of all water quality analyses by the National Accreditation Authority. This accreditation was a major step towards both legal acceptance and improved efficiency. It allowed a reduction in the reference analyses performed, thus reducing operational costs significantly. Through the standardization of both the instruments and their maintenance procedures, the total operational costs for online monitoring were reduced by 30% without buying a single new sensor. This results in a return on investment of less than 1 year. Further cost reductions are expected, resulting from a further reduction of second-level control measurements given the excellent performance of the online sensors. Currently, our example utility is in full transition towards remote-controlled routine operations with one central control room for treatment plant monitoring, and with this control room being staffed only during office hours. Aside from the cost savings, this also results in a considerable decrease of kilometers driven by staff, and thus a reduction of the utility's carbon footprint by about 17 kilotons of CO2 per year. Staff kilometers can account for up to 5% of the total carbon footprint of a wastewater utility. And this brings me to the fifth way to save costs, reducing staff workload. Automation processes can help to reduce workload by increasing productivity, for example, by making sure the number of kilometers driven by staff are reduced. Especially in the USA and Europe, changing demographics are the cause of an aging workforce, and public utilities often struggle to attract suitably qualified young talent. If staff shortage is already a problem, automation will help reduce the workload of the remaining staff so that fewer staff are necessary to accomplish the tasks. Available staff can focus on essential tasks while routine process monitoring is performed online. Staff will then receive a signal when human intervention is necessary. And as illustrated in the previous example, automation enables most staff members to work normal daily hours. Reduction of staff workload and limiting the irregular working hours comes with additional benefits of a reduction in staff kilometers driven and improved health of staff members. Aside from the estimated cost savings, which can be recovered in about 2 years, this also results in a modest reduction of a utility's carbon footprint. The sixth way to reduce costs involves the use of robots or underwater drones in sewer systems, which are either impossible or undesirable because of health and safety to enter. The aim of using robots is to prevent catastrophes, minimize emergency repairs, or perform damage assessments. The robots are fitted with 360-degree cameras, sensors, and GPS locators. They are usually connected to a laptop or a computer so that an operator can watch the camera footage in real time. Another option is shown here on the right, and that is to use aerial drones to detect sewage leakage from the air. Sewage generally has a slightly higher temperature than the surrounding soil of the pipelines, making it possible to detect leakages by means of specific heat patterns. The lifespan of sewer systems can easily be between 50 and 100 years. Important factors determining the deterioration rate of a pipe are its location and surroundings, its use, and the materials used in its construction. It is often assumed that the material of a pipe is the most important factor, but in reality, its location is more important. The location of a pipeline determines the minimum requirement for its condition. For example, if a pipe burst occurs underneath a busy street crossing with a lot of traffic, the damage will be greater than when a pipe burst occurs in an open field where the water can be drained more easily. Many water utilities operate on the basis of fault-induced maintenance. If a pipe burst occurs somewhere and is detected, a repair crew goes and fixes it. This is often the most economical way of performing maintenance. The alternative way is to perform maintenance at specific intervals. The difficulty with this, however, is the exact condition of a pipe, which is seldom known. Replacing pipe too early is economically unwise, but if maintenance intervals are too far apart, pipe bursts will happen in between maintenance intervals, forcing repair crews to take immediate action in between those maintenance intervals. Many sewer systems are inspected at regular intervals in order to determine whether repairs or replacements are necessary. However, despite the large number of inspections, the data collected during these inspections is often difficult to interpret and offer little information on the actual condition of the sewer pipelines. Now, sensor technologies can be very useful as rapid detectors of acute problems such as pipe bursts and leakage. However, online monitoring of the condition of pipelines in sewer systems, for example by measuring wall thickness, is considered unnecessary, as the deterioration rate of the pipe's condition is a slow process. It is, however, important to develop a clear strategy for inspections and maintenance in order to determine whether a pipeline's condition is indeed as expected. Specific events may cause increased deterioration, for example, industrial discharges of very acidic water. Data collection and storage is of vital importance to keep track of the condition of underground pipeline systems. The long lifespan of the system can make effective data collection and storage complicated. Data on inspections collected more than 25 years ago was stored either on paper or in older computer systems which may no longer be operational. The history of a pipeline is, however, of vital importance to optimize its maintenance strategy in the present. Thus, for regular maintenance and inspections, robotic aids and optimized software systems for the collection and assessment of inspection data are indispensable. Here are some figures from the UK. The actual costs of network improvements are difficult to determine. Sorry, that is not what I wanted to say. We're going to the figures from the UK here. The condition and performance of the majority of the buried water infrastructure in the UK is unknown, leading to reactive management of failure, greater costs and significant disruption. This lack of knowledge about the condition of buried pipes results in sporadic, unforeseen and creeping failures that may never be spotted. Locating and repairing these faults causes huge disruption to road traffic, pedestrians, city logistics and local businesses. There are an estimated 1.5 million road excavations per year in the UK, causing full or partial road closures. One moment, please. Excuse me for that. The actual costs of network improvements are difficult to determine, as I just said, as it depends a lot on the size of the network and the accessibility of the pipelines. Therefore, the figures presented here are for 1 kilometer of pipeline. Robots fitted with sensors can reduce the inspection costs by 30%. More accurate and efficient inspection will allow better preventive maintenance and thus reduce the costs of cleaning, restoration, and reconstruction, which together currently represent about 80% of the global cost of maintaining the network. The ROI is expected to be around 1 to 3 years, depending on how it's implemented. Aside from the cost savings, the reduction of excavations and emergency replacements of pipes can also reduce the utility's carbon footprint considerably. If 10% of emergency replacements can be avoided, this results in a carbon reduction of over 18,000 tons of CO2 per kilometer of pipeline. In summary, we've just seen 6 different ways to optimize wastewater treatment processes in order to save money and improve sustainability without having to make huge multi-million-dollar investments. And this brings me to the 7th way to save money and improve sustainability, by joining the Sensileau community. There you can find these and many other examples of utilities which have optimized their operations. We can learn from each other, so we do not need to reinvent the wheel over and over again. With the Sensileau Sensor Platform, we aim to empower water utilities through knowledge sharing. By connecting the global community of water experts, we inspire utilities to optimize their processes and to improve operations, save money, and reduce their carbon footprint. With our expertise, we aim to contribute to a more sustainable water industry, which is well prepared to face a future dominated by climate change challenges and increased water demand. We convert vast amounts of research reports and peer-reviewed literature into practical tools which support the successful implementation of sensor technologies. And in doing so, we minimize the time necessary to maximize the benefits from all available knowledge. Our goal is to make the worldwide water sector with all its municipal and private water utilities more sustainable and future-proof. But in order to achieve that, we need data. Or in the words of Lord Kelvin, you cannot improve what you cannot measure. Water quality monitoring is a means to an end, not a goal in itself. But when faced with major water challenges such as pollution or climate change effects, insight into water quality is essential to determine the extent of the problem and monitor the effects of measures taken. Without sensors, we are blind and deaf to what goes on in our water systems. Every water expert needs reliable data to check compliance with legal standards, control and optimize treatment processes, track leaks during transport, or determine the effects of effluent discharges. Thus, every water expert needs to know how sensor technologies can provide the necessary information to support action. However, data collection is just the beginning. By using sensors to measure water quality and quantity parameters, we collect data. Converting the data into information leads to understanding, but the information only becomes meaningful when put into context. Next, the combination of meaningful information and expertise leads to insights which enable us to make improvements. Let's look at an example. This graph shown here at the bottom depicts nitrate data. And the data have been split into 4 categories of increasing nitrate levels: 0 to 2, 2 to 5, 5 to 10, and 10 to 20 milligrams per liter. The graph suggests the geographical spread of nitrate data within a certain area. Looking closer, It turns out these data represent nitrate levels in drinking water in the state of Wisconsin, with the northern areas generally showing lower nitrate levels than the southern areas. As interesting as this is, when we put this information within the context of public health standards, it shows that the maximum allowed concentration by health standards is 10 milligrams per liter. So, all of a sudden, we do not simply have 4 categories of nitrate levels anymore, but now we have 3 categories which comply to the public health standards, and 1 category, the dark red one, showing where the limit value for nitrates in drinking water is exceeded beyond the legal limits. This provides the insight that within the state of Wisconsin, nitrate levels are too high in wells used by an estimated 94,000 households, as indicated by the dark red areas within the graph. This helps us to prioritize issues of major concern, identify what and where measures need to be taken, and how we can focus our efforts on achieving maximum results with our available resources. Sensileau supports this entire process by providing an elaborate sensor database to select suitable monitoring equipment and support successful implementation and operation in order to collect reliable data. Context is provided through the thematic approach we have chosen, covering the most urgent water challenges of the next 10 years. Insight is gained through the exchange of expertise and experience between users by means of real-life showcases. Sensileau's toolbox of step-by-step guides and calculation tools supports the prioritization process and suggests potential measures that can be taken to resolve the issues. Efforts are focused on achieving maximum results within the constraints of available resources, either through collective actions or one-on-one support. The costs to become a member of the Sensileau community are minimal as compared to the benefits that can be achieved if you are inspired by the examples we present to optimize treatment processes, save costs, and improve the sustainability of your plants. And by sharing the results of your own activities, you support others to make similar improvements. The Sensileau platform is a digital knowledge exchange platform, so you do not need to leave your office to have access to all the information available. This in itself already reduces your carbon footprint by 1 ton CO2 per year. And with this slide, I come to the end of my presentation. Thank you all very much for listening, and we look forward to welcoming you at the Sensileau Sensor Platform. Now
Oh,
back to you, David.
yeah, thank you, Karina. Somebody had texted in. Would it be possible for you to do a quick look at the Sensileau website? If so, we can pull over a share pod, and if you have a screen open, we can have you walk through what's available.
Yes, absolutely, we can do that.
Okay, let me pull over a share pod here. There we go. You might want to pause your recording. If you hover over your video screen, you'll see 2 little bars at the bottom left corner. Sometimes that just makes websites serve much better. So go ahead and share your screen.
Now I need to check which one is which to see which one I can share. Let's see what happens if I do this. Is this the wrong one or the right one?
Yeah, we're seeing your desktop at the moment.
Let me put this in
there. You go.
And if all went well, you should be able to see the Sensileau website, sensileau.app right now.
Yes, we do.
Yes. Well, to give you a quick overview of what we have, here are some of our partners that we work with. We have divided our Sensileau platform into various different thematic approaches. And as I said in the beginning, we cover both drinking water and wastewater themes. So depending on the utility of your interest, you may be interested in more drinking water focused themes or more wastewater focused themes. The themes that we currently have are based on a long-term study performed, for example, by the Water Research Foundation in the US and the Association of Water Utilities in Europe to identify the 10 most urgent water-related issues in the next 10 years. So we have minimizing water loss, which is mostly about leakage detection and finding solutions to that. Protecting water resources, which is one of the broadest themes that we have, which basically covers both surface waters and groundwaters in any type of pollution you might be able to think of. Boosting treatment efficiency, those are the examples that I have been talking about in the webinar mostly. Then we have water recycling possibilities. There's a number of water quality issues involved in water recycling issues. And very closely related to that is combating climate change, which is mostly about quality effects as a result of floods or droughts. The sixth one we have named Value Water, which is about, for example, citizen involvement and how to interest people into water quality and the water they use in and around the house to make them more aware of the challenges that utilities face in order to provide the water of suitable quality. And the last one is a bit an extraordinary one, which is attracting talent, which is more about the sensor technology and the possibilities it offers to attract young talent to this sector. Any of these, let me pick the boost treatment efficiency to stay in the same theme. When you click on any of the themes, you get an explanation of why it is important to think about it. You get some main figures of what we have found. And then there's a number of showcases that you can download from the website. They're all free to use and they are there to inspire other utilities to take actions in a similar way as these utilities have done. Some of the utilities have been named and have been located, and you can contact them directly. Other utilities have chosen to remain anonymous, and thus the names and their locations have been concealed, but we know who they are and we have checked the validity of the showcase they've shared with us. There are a number of questions you can answer to get some expert advice from us, and if you're interested, then you can go further to the actual content of the platform. So I am going to log in for a moment. This goes automatically for me because I am actually already logged in. And when you log in, you get the same themes that I just showed on the website here on the left, and you get a whole range of products, as you can see on the right, on the top. Now, the main flagship of our platform is the sensor database. I'll go to the database. And here in this graph, you can see a picture of the various locations at which we have sensors available to monitor water quality. That is source waters, meaning both surface and groundwaters, drinking water treatment, drinking water distribution, sewer systems influent, wastewater treatment plants, and wastewater effluent discharge. And number 7 is a complete overview of all the sensor information we have available. Now, for example, if I click on wastewater treatment, I get a pop-up screen with a list of parameters that are available that we have examined at this location in the water chain. And for example, we go to the nitrate measurements. Then you see a screen here on the right giving some basic information about nitrates, why you would be interested in measuring nitrates, first of all, during wastewater treatment, and what you could do with that information. Then we go to the next tab, which shows that there are 3 different kinds of principles that can be used in order to measure nitrate. The colorimetric method is the most well-known one, probably in most cases, and you get, for each you get an explanation. There's an electrochemical method using an ion selective electrode, and there is an optical method using UV light. Now, for each of these measurement principles, we have listed advantages of the method and disadvantages of the method and potential cross-sensitivities. We do that in order to ensure that the users can make an informed decision when they have decided to measure nitrates during wastewater treatment. You have to be able to make a decision on which method is the best. We cannot say upfront the optical method is better than the colorimetric method. We don't know that because the local conditions may be so that in this case electrochemical methods might be better. And therefore, we do not provide advice on what to use. We provide the information on the basis of which the user can determine for himself which method is the best applicable one. In addition to the advantages and disadvantages, we also provide information on costs, acquisition costs and operational costs, the expected instrument lifespan, and if we have sufficient information, we also give some information on user satisfaction. The next tab shows best practices. And again, they have been divided into the various different measurement principles available. And best practices show information that we have received from other utilities who have implemented this type of sensor. And it usually covers topics such as installation, operations and maintenance, calibration, the use of spare parts and consumable, and application areas. And then the last tab contains, again, by measurement principle, a list of suppliers of instrumentation. Again, we do not say you need to go and get it there or you need to go and get it there and this brand is better than that brand, because in most cases we are unable to determine that. If you have a utility which is filled with sensors from, for example, Haag, then it makes sense to get a nitrate sensor from Haag because that simplifies maintenance contracts and all kinds of other things if you already have other maintenance contracts for Haag instruments. If you have another brand, then you might want to stick with that one. Or if you're unhappy with that brand, you might want to switch to another one. So again, we provide all the information that we have available in order for users to take an informed decision about what they need and where they need it. And we have done this for a whole list of parameters. If I go to the complete overview, you can see that some of the parameters we're still working on, such as AOX, but we have a number of parameters, chemical parameters, event detection and toxicity, biological parameters and physical parameters, radiological parameters, and in the end also taste and odor. At the moment we have around about 75 different water quality parameters covered, and all in all roughly 650 different measurement principles and some 10,000 different instruments from various suppliers. That is one of the of the tools that we offer, another one that I would like to show are the step-by-step guides. For example, the wastewater treatment plant scan. It is based on a user case presented by earlier in this webinar. And it shows a graph like this, and it comes with an instruction to take the user through the entire process of doing a wastewater treatment plant scan. This is part 1, the effectivity analysis, and we have a part 2, which is the gap analysis. And it helps the user sort of redo what another utility has done in one of our showcases. And we hope that this kind of schematics inspire utilities again into taking actions as other utilities have done before. And we feel that this can be a very effective way of sharing knowledge without other utilities having to go through lengthy reports or working out for themselves what exactly they would need to do in order to translate the outcome of a showcase to their own utility. And one of the tools that is currently not there, but we're going to launch the first one in, if all goes well, in a few weeks, end of September, early October, is our calculation tool. And with the calculation tool, we offer a means for utilities to calculate what the potential effect of measures can be. For example, in the examples I showed during the webinar, we have used results that have been achieved at various utilities. But a commonly asked question, of course, for a utility operator is, yeah, that's all nice and well, but how does it work for me? For our utility, under our conditions, with our loads, etc., etc. So we have produced a calculation tool that will allow the user to include their own utility characteristics in order to calculate the potential benefits and costs, both in terms of money, dollars or euros, whatever, and for example, eco costs, carbon footprint, quality improvements, all different kinds of parameters to make sure that you can sort of compare various scenarios and work out if the benefits as described during the showcases will also have a beneficial effect at your own utility. This is just about what I would like to show you. Now let's see, how do we get back to the...
There you are.
There we are.
Okay, let me minimize the sleeve and move it away.
I hope that was clear.
It's a fantastic platform. I can't believe that people wouldn't get, as Mike Cook said, fantastic, well done, very practical. Real world examples are great. We all benefit when we all share. So are there any other questions coming in? The one that I did get by text, there was a posting actually on LinkedIn recently about the use of drone activated infrared scanning, heat sensor scanning, to look not just at water but at actual other transmission lines for cracks, leaks, remote spills.
Yes.
I think there's a lot of interest, at least I'm seeing a lot of interest in possibly hosting an event like that too. So if you have case studies where people have used drone activated overhead scanning, that would make, I think, a great presentation as well. Also recently had an inquiry for an event that we hosted several years ago actually about using iPads and connected sensor monitoring to monitor stormwater controls, where there were GPS chips. It's quite innovative. GPS chips located each of the known trouble spots so that the operator could actually be sitting there and scan the chip, put it into a GPS tracker, and enter data that was linked specifically to that by the square foot data point, which I thought was kind of interesting too. So this really does feed into the concept of smart controls, of smart water and wastewater. And I think this has been a really, really expansive and entertaining and very interesting presentation. Thank you so